Somebody once told me the world is gonna roll me. I ain't the Hello everyone, let's learn how to solve some equations. So, as a reminder, you can solve any equation by graphing both sides and seeing where they intersect using the intersection tool, and then looking at the x values, and those are your solutions to the equation. And I suggest throughout this video, if you have your calculator with you, you do that. You check all our work with that just to get some extra practice, and it'll help you understand the problem a little more. So the first type of equation we're going to learn how to solve are polynomials that aren't necessarily quadratics, but they are of the quadratic type. So what does that mean? If you have two variables, like a quadratic has x squared and x, and one variable is equal to another variable squared, like a quadratic in standard form where there's x squared and x squared is just x squared, then you can use the same strategies as a quadratic after doing a substitution. So what's a substitution? It's sometimes referred to as u substitution, but my u's look like a lot like a v sometimes, and I just think it's easier to write an a, so I use a substitution. So you look at the variable of the lower degree, set a equal to that, then square both sides, and a squared would equal the variable of the variable with the higher degree. Substitute in a and a squared, solve it like a quadratic, and then plug x back in. So that's what we're going to do right here. So we got two, the same variable x, but it comes up twice, once as x squared and once as x to the fourth. So we're going to use substitution. We're going to say, alright, a is equal to x squared, and then if I square both sides, I get x to the fourth is equal to a squared. So now I could take this equation and rewrite it as a squared minus 3a plus 2 equals 0. Then I could just solve it like a quadratic by factoring, and then I'm going to take this x squared and plug it back in for a. So I get x squared minus 2 equals 0, and x squared minus 1 equals 0. So I kind of did two steps in one there, substituting an x squared for a, and then setting each factor equal to 0. So you would get a is equal to 2 or 1, so that means x squared is equal to 2 or 1. So solving both of those equations now, you get x could be the square root of 2 or the square root of negative 2, or x could be 1 or negative 1 by just taking the square root of both sides here. Alright, so if it looks like a quadratic but it's not a quadratic, try doing substitution. Alright, next slide is how to solve polynomials not of the quadratic type. So let's say in the previous one I couldn't factor it. I could have done the quadratic formula and still done a substitution, or I could have done completing the square with a substitution. But other polynomials that aren't quadratics, if you can't do substitution to make it look like a quadratic, then you can't do things like quadratic formula or completing the square, extracting the root. But all polynomials you could factor. So if you get a polynomial, try to factor it first, and if you can't, see if it's of the quadratic type. So let's say you get something like this. This is a polynomial. It's a fourth degree, but you got x to the fourth, x cubed, x squared, and x. So we're not going to do substitution and treat this like a quadratic. We're going to get one side set equal to 0 and then factor by grouping. So I'm going to subtract that 6x squared on both sides and that 6x, and now I get this 4-term polynomial, and I notice everything is divisible by x, so I'm going to factor out an x. We do not want to divide both sides by x. We never want to do that. Then we're going to lose a solution. And actually, I should have factored out a 3x, so let me do that right now, because all these terms were divisible by x and 3. But again, we don't want to divide both sides of the equation by a variable. If we wanted to divide out a 3, we could, but that's because if we divide by a variable, we're going to lose a solution. Alright, so here's what it looks like after you pull out a 3x, and then now we're going to factor what's left inside by grouping. So we pull out an x squared here, and you get x plus 1, and pull out a negative 2 here, and you get x plus 1, and I don't know what this little thing is doing over here, so I'm going to erase it. Part of my 2 got erased. Alright, boom. And now, finish factor by grouping. So we get 3x times x plus 1 times x squared minus 2. Alright, oops, minus 2. So now, when we set each factor equal to 0, so we set this factor equal to 0, 3x, divide both sides by 3, and you get x is 0. Set this factor equal to 0, subtract 1 on both sides, and we get negative 1. Set this factor equal to 0, and we should get plus root 2 and negative root 2. You don't really need the plus, so you just say root 2. So those are 4 different solutions, and in general, for polynomials of degree n, you're going to get n solutions. Now that includes like repeated solutions, like you might get like one might come up twice. You could get imaginary solutions, those count. But in general, the fundamental theorem of algebra is that a polynomial of degree n will have n solutions. We'll spend a lot of time on that, but I just wanted to make you start thinking about that. So that's why a quadratic has 2 solutions. Yeah, sometimes it could have 1, but that would be a repeated solution. And sometimes it could have no real solutions, but it still has 2 imaginary. So this was a 4th degree polynomial that had 4 real solutions. It could have had 2 real and 2 imaginary, or 4 imaginary, but in general it should have 4 if the degree is 4. Alright, something to keep in mind moving forward. And like I said, we'll spend the whole chapter on that. Alright, next, equations with radicals or rational exponents. So the trick is we want to isolate the radical expression or the rational exponent expression. Then once we get that part alone, we're going to do an inverse operation on both sides. So like if you have x squared, we'll take the square root of both sides. If we have the square root of x, we'll square both sides. And keep doing this until there are no more radicals or rational exponents. And then just solve for x. So let's do one of each, a radical equation and a rational exponent equation. So here's the first one. So first thing we're going to do is isolate the rational exponent expression, which is this part right here. So we're going to do that by adding 17 to both sides. So you get 3 times x plus 2 to the 3 over 2 power equals 48. And then divide both sides by 3. And you get x plus 2 to the 3 over 2 power equals 48. Not 48, 16, because we divided both sides by 3. Alright, now to get rid of this 3 over 2 power, we're going to raise both sides to the 2 over 3 power. 2 over 3 power. And that cancels out over here. So this becomes like x plus 2 to the 6 over 6 power. So it's like x plus 2 to the first power. So it's just x plus 2. Then here we have 16 to the 2/3 power. Now I'll admit when I made this problem, I should have made this original 3 over 2, 2 over 3. So when I got rid of it, I would have been taking the 3/2 power both sides, giving me a 64. But I didn't. So instead we get this irrational number right here, 16 to the 2/3 power. So we're just going to subtract 2 on both sides. Not the end of the world. We just get a weird answer. And we get negative 2 plus 16 to the 2/3 power. And then you could just type that in a calculator. And 16 to the 2/3 power, let's see what that comes out to. So 16 to the 2/3 power comes out to 6.34. So if you add 2 to it, x would be approximately 8.34. But if I was asking you to give me an exact answer, then you can write it like we have below, or as like the cube root of 16 squared minus 2. I mean, either one's fine. But a lot of times this part, you'll be able to evaluate it without a calculator. But if not, then you just leave it, or if you have a calculator, then plug it in. Alright, let's look at a radical equation. So we have 2 radical expressions. We have the square root of 2x minus 5 and the square root of x minus 3. So we have to get one of them alone and then square both sides. So let's get this alone first. So we'll get the square root of 2x minus 5 is equal to root x minus 3 plus 1. So now we're going to square both sides. So we're going to raise both sides to the second power. So boom, and then boom. And then the left side is nice. That'll just cancel out the radical and the square, and you'll get 2x minus 5 on the left. On the right, that's two terms being squared, so a binomial square, which means we have to FOIL it out. So it's like root x minus 3 plus 1 times root x minus 3 plus 1. So root x minus 3 times root x minus 3 is x minus 3. And then root x minus 3 plus 1 is root x minus 3. When we do the outers. And then the inners also gives us root x minus 3. So we'll have 2 root x minus 3. And then plus 1. Now we want to get this radical expression alone. So we went from 2 radical expressions to 1. So now we have to isolate that. So if we combine the negative 3 and the 1, that would be a negative 2. So if we add 2 to both sides, that'll get rid of it here. And subtract x on both sides, that'll get rid of that there. So you'd get x minus 3 is equal to 2 root x minus 3. So if we divide both sides by 2, we get x minus 3 over 2 equals the square root of x minus 3. Now we could square both sides and get rid of the last radical. So that's why I have to get rid of one at a time. Alright, so then we're going to be over here. We're going to have x minus 3 squared, which is x squared minus 6x plus 9 over 4 is equal to x minus 3. And then we're going to add 3 to both sides, which is the same thing as adding 12 over 4 to both sides, because that's when you get a common denominator, and you get x is equal to x squared minus 6, and then 9 plus 12 is 21, so you get plus 21 over 4. And I should be getting 0 on one side, so we should also subtract x on both sides. So we could actually just cross multiply, and we'd get 4x is equal to x squared minus 6x plus 21. And then if you subtract 4x on both sides, you'll get x squared minus 10x minus 21. Then if we factor, we get x minus 7 times x minus 3. Nope, that's not true. Hold on, I'm going to pause this real quick. I see what I did. I never put the plus sign when I rewrote the equation because I was running out of room. So it should be x minus 7 times x minus 3 is equal to 0. And then you get x is equal to 7 and 3. And then you should plug those back in, make sure they work, and if they don't, then there's no solution. Because a lot of times when you square both sides, you create extraneous solutions. Just look at, well, I'll show you why in a second, but if we plug in 7, we would get 2 times 7, which is 14, minus 5 is 9, square root of that is 3, minus the square root of 7 minus 3 is 4, square root of that's 2. So you get 3 minus 2 is 1. But if you plug in 3, it would also work. You would get 6 minus 5 is 1, square root of 1 is 1, minus 0. So both of these are solutions, 7 and 3. But just to show you an example of when you might get, or why you might get an extraneous solution, if you think of x equals 1, right? We have one solution to that. But when you square both sides, now you have x squared equals 1. And then take the square root of both sides. Now your solutions are x is 1 and negative 1. But originally, the only solution was 1. So see, by squaring both sides, we create an extraneous solution. So that could happen when you square both sides. So always check your work, especially when you are squaring both sides. Alright, we did a little bit of this before, but let's do it again. Rational equations. So that's when you have variables in your denominator, and we're going to solve that by multiplying everything by the LCD and then simplifying, or we can get common denominators and cross multiply. So both work. Certain times it's easier to do one thing versus the other. I like to multiply everything by the LCD. Seems to like it'll work here. So the LCD is going to be x times x minus 3, because that's this denominator factored, and x comes up there and there. So if we multiply each term by that, and then here x times x minus 3, and then that times that, you'll see, alright, starting from left to right, these x's cancel out. So we have x minus 3 times x plus 2, which is x squared minus x minus 6. And then these x's cancel out. And then x minus 1 times x minus 3 is going to be equal to x squared minus 4x plus 3. And then these will cancel out, giving you 4x or minus 4x plus 2. So be careful if you got a minus in front of a fraction. You got to distribute that to every term in the denominator, in the numerator. So now, these x's cancel out, and then if we simplify, or those x squareds cancel out, you get negative x minus 6 is equal to negative 8x, and then 3 minus 2 is 1. And then if you add 8x to both sides, you get 7x on the left. If you add 6 to both sides, you get 7. And then x is equal to 1. And then if you plug that back in, you won't have any domain restrictions. So that's your solution right there. Last but not least, absolute value equations. So the way to do this is rewrite the equation in two different forms. One where what's inside the absolute value is positive, and one where what's inside the absolute value is negative. Because remember, like, if you had like root x is equal to 3, not root x, the absolute value of x equals 3. Like, x could be 3 or x could be negative 3, because the absolute value of both comes out to 3. So vice versa, if you have the absolute value of x is equal to something, you could just rewrite the equation, one with a negative and one with a positive, in front of the expression that was inside the absolute values. So here we're going to break it up as, okay, x squared minus 3x is equal to negative 4x plus 6. Well, I know if x squared minus 3x is just x squared minus 3x, then the original equation without the absolute values is still going to be true. Or if it was negative x squared minus 3x, the absolute value of that would become positive x squared minus 3x. And we'd set that equal to negative 4x plus 6. So now we solve both equations. So here we're going to get x squared plus x minus 6 is equal to 0. And that gives us solutions of factors of x plus 3 and x minus 2, which gives us solutions of x equals negative 3 or 2. And then here, if we solve this quadratic, we get negative x squared plus 3x equals negative 4x plus 6. Get everything over to the right side, and we get x squared minus 7x plus 6. And if we factor, we get x minus 6 times x minus 1. And we get two more solutions of x equals 6 or 1. Oops. So if you look at our graph, we'll see that the graph only shows two solutions. So it shows why it's important to plug these numbers back in. That's because, well, first, out of the 4 solutions we got, the only 2 that should work are 0 and negative 3. The reason why that happened is because if we look back at the definition of an absolute value, the absolute value of x will equal x only if x is greater than 0. And likewise, it'll only equal negative x if x is less than 0. So if we made one side of the equation like negative, like when we put the negative in front of x squared minus 3x, that's only true if x is less than 0. So if we got solutions that were greater than 0 there, then they're going to be extraneous. Likewise, if we just made x equal to x and we got solutions that were less than 0, then that wouldn't work because absolute value of x only equals x when x is greater than 0. So moral of the story is just make sure you plug these answers back in, make sure they make sense. Alright, that's the end of the video. Hope you found it helpful, and please let me know if you have questions. Thanks for watching.